Hello everybody, this is the video for lesson 4.6, which is solving application problems that involve exponential models. We're going to see a couple of different types of exponential situations, exponential growth and exponential decay. And again, at various points in this video, you're going to want to pause so you can write stuff down, make sure you have a good set of notes. The first type of problem we're going to look at, we've seen before actually. It's continuously compounding interest, which uses this formula here. And remember, P stands for principal investment, R is interest rate, T is time. We've used this formula earlier in this chapter to solve for a future amount, A. We're going to change things up now and solve for one of the variables in the exponent, either rate or time, which is going to involve logarithms. This first example, go ahead and pause this now so you can write this down. Okay, the key words here is that it's compounding continuously, which is an indication of the use of that formula there. And the other indication that's important, or the other phrase, is how long will it take? How long will it take is an indication that you're solving for a value of time. So we're solving for a value of t, which means we have to have values for all of the other variables there. So the principal investment was $8,000. The rate was 0.04. And then it asks how long does it take for it to double. So the future amount is double what you start with, which is 16,000. So with that information, we need to create this function here to be able to solve for t. So 16,000 is a future amount. Principal investment is 8,000 times E, and the rate is 0.04 times t. So we've set up our model, or our function now. We just got to solve this equation for t, and you notice that the variable is in the exponent, which makes this an exponential equation. That's what we studied in the previous section, section 4.5. Solving exponential equations involves usually three basic steps: isolate the exponential term, use a logarithm on both sides, and then solve for the variable. So isolating the exponential term, which is e to the 0.04t, that's the exponential term there, we're going to divide by 8,000 on both sides. So now that the exponential term is isolated, we can use a logarithm. In this case, since we have base e, we're going to use a logarithm with a base e, or natural log on both sides. So natural log cancels base e, and what we have is now natural log of 2 equals 0.04t. So now we're to step 3, which is solve for the variable. So divide by 0.04. So the amount of time it takes for that investment to double is natural log of 2 divided by 0.04. So looking on a calculator now, natural log of 2 divided by 0.04 is 17.33 years. So a variation you may expect or may want to be prepared for in a problem like this is rather than solving for how long it takes for an investment to double. They may give you a situation where they want the investment to double in 10 years. What should the interest rate be? In that case, you'd be solving for the rate, but the process would be very similar to what we just did. It would just be nothing more than solving an exponential function or exponential equation. Another type of exponential growth situation that has a different model is specifically when you've been given an observed doubling time. For example, you start with a count of 10,000 bacteria and it doubles every 50 minutes. How much bacteria will there be in 10 hours? Something like that. Where there's a specific observed doubling time given, you would use this model right here. Notice it has a base of 2, which is an indication that it's doubling every so often. So go ahead and pause this and jot down this model and the information there. The initial amount is a sub 0, t is time, x would be the doubling time. So an example of what this would look like, go ahead and pause also and write this down. So some of the key indicators here that you would use this doubling time model, obviously it says here that this doubles every 90 minutes. So it's giving us an observed doubling time, and it's asking us to create a function that models that situation, and then use the function to estimate the number after 10 hours. So using this model, the initial amount is 1,000. And the doubling time, x, is 90 minutes. So this is our model, 1,000 times 2 to the t over 9, 90. So that answers the first part of this, which is find a function that models the amount of bacteria at any time t. This is it right here. The key, though, is using that model to make predictions. That's what scientists do. They create models to model situations, and then they use that model to make predictions or to answer questions. Now, one common mistake that students make in a problem like this is mixing units of measure of time. What I mean is the doubling time they've been given is 90 minutes, but it's asking us to find a number after 10 hours. Hours and minutes are different measurements of time. So we've got to make sure that those match. I wouldn't plug in 10 for t because that's in terms of hours, and the doubling time here, 90, is in terms of minutes. So 10 hours is 600 minutes. I'm going to use 600 minutes rather than 10 hours because that's going to match my doubling time unit of measure. So the amount after 600 hours is equal to 1,000 times 2 to the 600 over 90. And this is now a calculator problem. So 2 raised to a power of 600 over 90 is 101.59. We times that by 1,000. We get 101,594. I'm going to round up to the nearest whole number because we're not counting half of a bacteria. So again, the key takeaway for a problem like this is noticing which specific type of function is appropriate given the information. In this case, since we were giving doubling time, specific doubling time, this model was appropriate because that involves a specific doubling time. And the other key here is to anticipate that you may have different units of measurement for time and to make those match. That's a very common mistake students make. Another situation that involves exponential growth is when you are given an observed what's called a relative growth rate. For example, a population of deer is observed to have a count of, let's say, 1,000, and it's observed that the population increases at a rate of 7% per year, something like that. That would be, rather than giving us a doubling time, that would be giving us a relative growth rate. So we would use a different model. This model here represents exponential growth when we've been given a relative growth rate. So go ahead and pause, write down the function, write down this information. Now this function does certainly look different than the ones we've been using, but actually this particular function is no different than this model here, where P is the initial investment or principal investment. Here A sub 0 is just the initial count, R is the interest rate, here K is the relative growth rate. So this function is really nothing more than continuously compounding interest, if you want to think about it this way. So an example here, a population of frogs, let's say in a forest, I don't know where, but a population of frogs is observed to have an initial count of 2,500 frogs, and it increases at a rate of 5% per year. Go ahead and pause so you can write this down. Our task is to find a function that models the number of frogs at any time, and then use that model to predict the number of frogs in 5 years. Since we have not been given a specific doubling time, but we do have a relative growth rate, we can use this model. The amount at any time t is equal to the initial amount times e to the kt, where the initial amount is 2,500, relative growth rate is 0.05. So then the model would be a of t plus 2,500 e to the 0.05 t. So this here is the model that they asked for. You can use this model to make predictions now, or to make estimates for some future amount of time, in this case 5 years. So now use this model to predict the number of frogs in 5 years. All we got to do is plug in a value for time, in this case 5, and run it through a calculator. So the amount after 5 years, 2,500 e to 0.05 times 5. So e to the 0.05 times 5 is 1.28. And then we're going to multiply that by 2,500. So 3,210 roughly. And again, we're not going to count halves or decimals values of frogs. So 3,210 frogs. We started with 2,500. After 5 years, it's grown to 3,210. So the key takeaway for this problem is recognizing that since we weren't given a specific doubling time, we used a different model, which was really just continuously compounding interest in a way, where we've been given a relative growth rate and an initial count. The last type of exponential situation we're going to look at is an exponential decay, specifically radioactive decay. And this is very similar to doubling time, because most often when dealing with radioactive isotopes or substances, a half-life is given, a specific half-life. So in that situation where we have radioactive material and a given specific half-life, we use this model. So go ahead and pause, write down this information. Now, as an example, this radioactive isotope cesium-137 has a half-life of 30 years. Let's suppose we have a 10-gram sample. How much is left after 20 years? So since we've been given a specific half-life of 30 years, we can use this model. The amount at any time t is equal to the initial amount times 1/2 to the t over x, where the initial amount is 10 grams and the doubling time is 30 years. So then the model is a of t equals 10 times 1/2 to the t over 30. So that's the model we now use to answer the question, how much is left after 20 years? That's just simply plugging in a value of time for t. So the amount after 20 years is 10 times 1/2 to the 20 over 30. And again, this is a calculated problem. So a base of 1/2 raised to 20 divided by 30, 0.629. And that's going to be multiplied by the initial amount, 10 grams. So 6.3 grams. So those are examples of the several different types of exponential situations: exponential growth involving compound interest, exponential growth involving doubling time or relative growth rate, and then radioactive decay involving a half-life.